So welcome everyone to the second lecture in our series on PCP theorems. So today we're very happy to have Dana Moshkovitz from the University of Texas at Austin, an expert on PCP theorems and their applications, to tell us how to prove a weak version of the PCP theorem.
Okay, thank you so much, Joe. Okay, so I will show a proof of a weak PCP theorem, a proof that will hopefully more or less fit in 1 hour. I'll try to do it the traditional way, questions and answers. I'll do the traditional way this time. So after I discuss something, I'll just pause for questions and try to answer the ones that accumulated. Okay, so Irit presented the PCP theorem yesterday. So PCP means probabilistically checkable proofs. And it has many different formulations. And the formulation that she gave was as follows. You can take a graph, any graph G, and you can, in polynomial time, convert it into a graph G tilde, and such that if if G is what's going on? If G is three-colorable, then so is G tilde. And meanwhile, if G is not three-colorable, G tilde is far from three-colorable, in the sense that for every coloring of the vertices, at least 0.01 fraction of edges monochromatic, so they witness that this is not a good coloring. Okay. If the graph is not three-colorable, it just means that for every coloring there exists an edge that is not colored right. And suddenly here, for G tilde, not only there exists one edge, there exists many edges. So constant fraction of the edges are monochromatic. And this transformation from G to G tilde is polynomial time. It means in particular that we consider G tildes that are polynomial size. No one knows how to efficiently figure out whether G is three-colorable or not. And yet we have this transformation that makes the fact that the graph is not three-colorable manifest in a very large way. Okay, so for G, you're given a coloring. You really have to go over the entire coloring to check it, and for G tilde, you don't need to go over the entire coloring. It's enough to pick a random edge and check if it's good, check if it's multichromatic, bichromatic, and if it's good, then you're reasonably likely that we're in the first case of G tilde is three-colorable and not in the second case. And of course, you can repeat this test many times, right? Repeat it like 100 or 1,000 times, and you can get pretty much sure that we're probably in the right. If they're all colored right, all those random edges, then you get pretty sure that you're in the three-colorable case and not in the second case. Okay. So this is this amazing theorem, More generally, what's happening here is that we have a global property. And the global property here is G is a three-colorable. So this is a property that is right. You have to, given a coloring, you have to go and check everything. And then you somehow are able to test it with a local test. Okay, so the local test here is like pick a random edge in G tilde and check. Okay. Now, there are many different formulations of the PCP theorem, many different PCP theorems, and different PCP theorems consider different global properties and also different local tests. And accordingly, they achieve different parameters. So we can start with talking about the global property. So here G is three-colorable, but more generally, so Erik mentioned, it's every property of the form. There exists some solution for your input such that it satisfies something that can be checked in polynomial time. Okay, so anything that can be formulated like that, this is what we call NP languages. You can choose as your global property, right? So G is three-colorable. There exists a coloring such that all the edges are colored right. But you can pick anything, right? Your input can be a number n, and your y can be some possible mathematical proof, and AY can check whether this is a valid proof of size n to the Riemann hypothesis. Right, so this is also applicable if someone comes to you and says, I found a proof for the Riemann hypothesis with maybe a computer, and the proof is many terabytes, and you want to check it, and kind of you don't know how to go about checking the original proof. It's so large to even just store. But suddenly with this PCP theorem, if only this person wrote the proof, apply this transformation, you can now test it in a local way. And here here it was coloring with G tilde, but in general we can try to have all kinds of local tests, and local tests can differ in what we call the number of queries or the number of proof locations that we consider. Here it's 2, but it doesn't have to be 2. It can be 3 or 4 or 10 or maybe even more. Though usually 2 is enough. It can be different in what we call the alphabet, which here is the number of colors, and it's 3, but the alphabet can be larger, and it can differ in which predicate you test. So here it's whether the edge is bichromatic or not, but it could be any predicate you want on those queries that you make. The issue is that it's local. The issue is that we look at a small number of places in this transformed graph or transformed input. Okay, so I see a question. Can the PCP theorem itself be formulated in the NP language? Yes, I think that this is something that appeared, question that appeared. Well, I'll try to answer it. I'm not sure that I understand it right, but yes. In particular, right here, we're talking about the 3-coloring problem, right? So in particular, here we're talking about an NP language. And this proof, which is a 3-coloring here, right, is also a legitimate NP proof. Okay, so yes, right. So we start with an NP property here, and we end up with an NP property here, but it's a much more robust property, right? Here, it's enough to check randomly small local test and still know whether this big global property holds or not with good probability. Okay, so I hope that this answers the question. If there are any other questions, let me say one more thing that people asked yesterday. What's the point with this 0.001, right? So obviously it's arbitrary, but you couldn't put here, you know, something much larger, right? When you talk about free coloring. So once you decide on what's your number of queries and what's your alphabet and what's your predicate, there is some number that you can put here that is the right number. So for example, for free coloring, if I just picked my coloring completely at random, right? So each vertex I assigned a random coloring. Then with probability, the probability that if I look at one edge, that the edge is not colored right, is just 1/3. Okay, so it's every graph basically has a coloring that with 1/3 here. So I mean, I can't prove this for something better than that. Okay, but yeah, if you want to put here something very close to 1, you can, but then the number of queries, the alphabet, and the predicate should be accordingly. And the amazing thing is that you can keep the number of queries too, and fine, you increase the alphabet. If this is epsilon, maybe the alphabet needs to be like 1/epsilon or something, but the predicate needs to be like a different predicate than free coloring. But you can actually achieve here whatever the error probability can be extremely small, even with just 2 queries in the local test. Okay, so let me see what new questions I got. Are the monochromatic edges in G tilde evenly distributed among the edges of the graph? So what I told you, it's a 0.01 fraction, right? So you pick a uniform edge, and right, you have this constant probability to get it. Yeah, and you can prove all kinds of theorems that show that, right, you can do all kinds of transformations that ensure various even distribution of the bed edges. Right, so different PCP theorems also differ in you know, you can get all kinds of extra properties on properties of the graph, like degree, or properties of you know, where the bed edges are. Are they supported on most vertices and so on? Yeah, so you can assume even distribution. Weak, yeah, I'll explain. Right now I only stated the normal PCP theorem. I can actually even explain it now. So the weakness would be that I won't show a polynomial transformation. What I'll show is that I can generate a random edge here in polynomial time. Okay, the graph itself that I'll construct today is going to be of exponential size in G, but I'll be able to pick a random edge from G tilde in polynomial time. Okay, so this is not what's promised. We can actually prove what's promised, but right, I'm trying to do something that can fit in an hour. Okay, if this didn't answer the question, yeah, okay, hopefully question, yeah, right, I answered the question of what's weak. It's not going to be a polynomial time transformation today, just random edge is going to be generated in polynomial time. Good. Okay, so hopefully we know what we'll try to prove. I want to say something more about what I'll try to prove. How do you? So as I said, you can change the global property and the local test, and different PCP theorems differ in different choices of the global property and the local test. The choice of the global property, yeah, so this is just a kind of a matter of convenience, the kind of equivalence between different global properties, at least up to polynomial time computation. This is the magnificent theory of NP-completeness that we have in theoretical computer science. The specific global property that I'm going to consider, both as global and as local, is quadratic equations. Quadratic equations over 0, 1. So what I mean is mod 2. Okay, so the computational problem I'm going to consider. So you're given a bunch of quadratic equations. So polynomials of degree at most 2, things like x1 times x2 plus x2 times x3 plus, maybe x1 plus x5 and so on, plus 1 equals 0, right? So I'm given a bunch of equations like that, and I'm trying to find the solution. So an assignment of 0, 1, right? So everything is mod 2, right? That's why I never have x1 squared, because x1 squared is just x1. I never have minus, right? Because minus is plus, right? So I walk over mod 2. I have n variables, x1 to xn, and I have a bunch of equations like this of degree at most 2, and I'm trying to figure out whether they have a solution. So this is the problem that I'll use. And what I'm going to show is I start with this system of quadratic equations like this, and I'm going to transform it to this squiggly, this tilde system of equations. And the thing is that here, each equation depends on 3 variables. Okay, so for the initial system of quadratic equations, the equations can depend, each one can depend maybe on all variables, on many of the variables, and in the new system, each equation is, right, it's a sparse system, so each equation only depends on 3 variables, so 3 bits, which is minimum. And as I said, this transformation that I'm going to define is not going to be polynomial. In fact, right, this is the weak. This E tilde is going to be huge. It's going to be exponential in the size of E, but each equation will be generated. Random equation will be generated in polynomial time. Okay, so we'll show. So this is the weak aspect. We'll show how to generate an equation in E tilde in polynomial time. And instead of not logarithmic time. And if you actually want E tilde to be the same, to be polynomial size, you really need to be able to generate it in order log n time, order log E time. And this I won't be able to do with the construction I'll show you today. But what I'll show is, again, those 2 bullet points. If E is what we call satisfiable, so there exists some x, some assignment to the variables that satisfies each and every equation, then also E tilde is satisfiable fully, whereas if E is not satisfiable, then E tilde is far from satisfiable. That is, for every assignment, to x1 and x2 xn, at least 0.01 fraction of equations of force. And by kind of standard ideas of NP completeness, you could have, I mean, I'll show you this theorem, but you could have cast it in the language of free coloring, like in its formulation, maybe with some loss to parameters. Let's see, what are my questions? Each equation in E tilde is generated in polynomial time, but E tilde itself takes exponential time to generate because there are exponentially more equations. That's true. Good. Polynomial here refers to polynomial in the number of variables. So the log of number of variables, wait, so polynomial, where did I use polynomial? In the, it's polynomial time in the size of E. So I assume that I start with a system of equations with n variables and say order n equations. And now I can generate each equation in polynomial time in n. Hopefully this answers the question. Is there any relation between the satisfying solutions of E and E tilde? Yes. So what we'll show is that we can start with, so if we start with a satisfying solution for E, we can use it, encode it to get a satisfying solution to E tilde. And vice versa, if you have a solution to E tilde that satisfies a huge number of the equations, then we can construct from it a solution that fully satisfies E. All the proofs I'll show you are constructive. More questions? Yeah, I think that I answered the questions. Okay. Can G tilde, E tilde, be allowed to satisfy at least 0.99 fraction of edges instead of being three colorable? So this is what I said in the previous slide. So free coloring was some choice, a static choice. And here it will be more convenient for me to work with quadratic equations. So this is what I'll do. And you can move from quadratic equations to coloring, from coloring to quadratic equations. So this is the nice theory of NP completeness. There are transformations between each two. If you don't care about what happens to the fraction, it's quite easy to move between the two. Okay, good. So hopefully now we are all sure what we're going to do today. In the I guess a bit more than half an hour that I have. Okay, good. So let's start a new whiteboard. Okay. So I'm just going to jump to it and show you the construction. Let me say a few more things before I do that. So I'll show you quite simple construction. It gives you some flavor for the actual proof of the PCP theorem, but to actually prove the PCP theorem, you need to work much harder. This is one thing. There are two more reasons to show you this simple construction. One is that the simple construction, there are actually applications of PCP, like in practice, to verify things quickly. And right, you can find it Mozilla, and people try to put it on blockchains and stuff. So often what's used in practice is actually this simple construction that I'll show you. And the other thing is that each and every proof of the PCP theorem actually has inside of it either the construction I show you or a related construction. Okay, so I'm not showing you something that is unrelated to anything. It's actually essentially inside each and every PCP construction. See that there are more questions. Is the actual construction of E tilde important, or is the mapping from E to E tilde important? The fact that there is a mapping from E to E tilde is the PCP theorem. I will show you the construction. I think that there is a lot to learn from it, and it gives you kind of a feel for whether, for how this can be true. Okay, right. The PCP theorem says something quite extraordinary. That someone has a huge proof for, say, the Riemann hypothesis. They can write it in a different format, and suddenly you'll be able to check it probabilistically by looking only at a few bits in the proof, right? This is this crazy statement, and it's unclear that it can be true, and hopefully you'll get a feel for how it could be true from this lecture. So let's look at the construction. So here is the construction. Okay, so I assume that the system I started with of linear equations. So we start with E, and I assume on the variables are x1 to xn, and with equations E1 equals 0 until EM equals 0. Okay, and without loss of generality, M and N are the same order of magnitude. And now I want to define for you E tilde. Okay, so E tilde has a variable for every quadratic polynomial Q that takes 0, 1 to the n and gives 0, 1. Okay, so here quadratic means degree at most 2. So it can be linear, it can be, constants are not very interesting, but okay, so every quadratic polynomial, and let me just say, a quadratic polynomial is given by this coefficient, right? So qx equals some qij xi xj, and it's possible. Let's define that x0 is defined to be 1. So this encapsulates also the linear functions. Okay. So for every quadratic polynomial, I'm going to have a variable, right? So you already see that E tilde is huge with respect to E, right? Because the number of quadratic polynomials, right, this is like 2 to the n squared. Okay, but fine, I can generate each one in polynomial time. And I'm going to denote it qx, and what I mean is that what I want this variable to be assigned is, there is x that is supposed to be the satisfying assignment to E. And what I'll ask the prover, right, is take this x, a good assignment for E, and evaluate Q on this X that you have in mind. Okay, so it's supposed to be Q of X for some X, because what the prover can do is completely ignore what I ask him to do or her to do, and give me any assignment to QX. But I remember I put it in quote to remember that this is what I expected to be there, and the quote mean that maybe this is not what's going to be there. So this is a notation that I find useful. Okay, so these are the variables in ETIL. Okay, so now I need to define for you the equations, and what I'll do is I'll just show you how to pick a random equation in ETIL. Okay, so pick a random equation in ETIL by doing the following procedure. So I'm actually going to have like four types of equations. And the first type, so this is with probability quarter. I do the following. I'm going to pick linear L1 and L2 from 0, 1 to the end to 0, 1. And I'm going to check the linear polynomials. Right, I said that quadratic polynomials for me are any polynomials of degree most 2, in particular all the linear polynomials. So the linear polynomials are linear. So I would expect L1 of X plus L2 of X to be L1 plus L2 of X. Right? I mean, if what the prover actually did, if the assignment is actually, you have your X and you give each polynomial, each L just gets L of X, then indeed this equality holds. So let me test that this happens. Okay. If there are any questions, the second test, again with probability, everything is going to happen with probability a quarter. So we do the same thing. Also, the family of quadratic polynomials is linear, so I'm going to do the same thing. Pick quadratic, and Q1 and Q2. From 0, 1 to the end to 0, 1, and I'm going to check the same, right? Q1x plus Q2x equals Q1 and plus Q2. I mean, maybe someone might wonder, why do I need both 1 and 2? Because obviously 2 subsumes 1. But the issue is that when you pick quadratic polynomials, most of the time you don't pick linear polynomials, because there are many more higher degree than the linear, and kind of 1 guarantees that there will be good properties for those linear polynomials. And 2 just will guarantee something for the degree 2 polynomials. Okay. So this is my second test with probability a quarter. I'm going to check the relation between the Q's and the L's. We're going to pick linear L1, L2, but now I'm going to check that L1x times L2x equals L1 times L2 x. So finally, I do this right on the right hand side. I have a quadratic polynomial. On the left hand side, I have the multiplication of 2 linear polynomials. So kind of I compare consistency between the linear and the quadratic polynomials, right? And obviously, if everything, if there are no quotes, then everything should hold. So it makes sense to check it when there are quotes. And finally, so notice that so far all I'm trying to do is I'm trying to make sure that the assignment to the variables of E tilde looks indeed like what it's supposed to be, like Q of X, right? So every polynomial Q is assigned the evaluation of Q on this good solution, right? So I'm trying to force the assignment to actually resemble the intended assignment. And I haven't checked at all any of the equations in E. So this is what I'll try to do now. So again, with probability a quarter, I'm going to pick, so I'm going to pick two things. I'm going to pick R1 to Rm in 0, 1. And I'm going to pick a quadratic Q. And I'm going to check. So I'm going to look at the linear combination, Ri, Ei. Right, so all my EIs, right? So these are the equations from E, the original equations that I actually care about. Oh, wow, you can't see the bottom of my screen for some reason. Right, this is, okay, let me, I can try to write it on the side. I did not expect that you won't be able to.
So I can see up to and including the bit that says sum of Ri and Ei.
Oh, you can see.
I don't know if there's anything below that, but that's what I can see.
Oh, because I cannot see it on my screen.
I can only speak for myself. But...
Okay, so let me use, yeah, on the iPad, right? I can actually, I have another line to write. So let me use it. So I'm going to look at this random linear combination of my equations from E. And I'm going to look at this plus Q, right? So this is some quadratic polynomial. And right, which I want to evaluate on X, and I'm going to make sure. So remember that I assume without loss of generality that all my equations are E1 equals 0, E2 equals 0, and so on and so on. So really, so this linear combination is supposed to be 0 if I actually have an assignment that satisfies all the equations. So this is supposed to be QX. So let me check. Okay, good. So now let me answer questions. How to randomly pick some equations that satisfy certain properties? I don't understand. Right, I just defined for you how to pick a random equation. So with probability quarter, you do what's in 1. With probability quarter, you do what's in 2. So right, each one of them is an equation on at most 3 variables in my system. Okay, so I just defined for you everything.
Dana, can I ask you a question?
Sure, please.
I thought you wanted to make the new equations sparse. So 1, 2, and 3 are sparse, but the fourth one seems to involve just as many variables as there are equations in the original.
No, it involves only 2 variables. Right, notice.
I thought that each EI would have been its own variable in your new
system.
Yeah.
Each EI
so there are at least m variables in this equation, right?
Wait. Each EI is its own variable. However, also the linear combination of all the EIs plus Q is also its own variable.
Okay.
So I think maybe a point of confusion for some people, because I've also had some chats, is that when you write a polynomial in quotes, it's not really the polynomial; it's the input variable to the E tilde, to the equation of E tilde.
Right. So E tilde.
So everything in quotes is one variable
for every quadratic polynomial, and this I denoted by this. And it's just the name of the variable, right? The variable is getting a bit. The bit can be anything, but what I expect, I do this because I want to say, I expect this variable to be assigned the quadratic polynomial evaluated on the good X that's supposed to exist for me.
Great, thanks.
Okay. We have more questions. What does L1 plus L2x means? It seems to me that L1 plus L2x. Yeah, again, so all the equations I wrote down are equations that without the quotes obviously hold. But the issue is that when I put the quote, this is just the name of the variable that is supposed to be assigned this. So, and the variable could be assigned anything, right? So with the quotes, I mean, it's not clear if it holds, but hopefully what I'll show is that if it holds with good probability, with high probability, then my assignment actually can be decoded to a good assignment for E. Okay. How does the variable in E tilde depends on the input X? So let me, I understand that there is one variable for each quadratic, but is there also one for each assignment to the variables? No. So we take E, and hopefully E has one assignment to the X's that satisfies all the equations. It may have more, right? But it should have at least, right? If we're in the situation where there is a solution to E, then there exists some X that satisfies all the equations. So what I'm going to ask the assignment to E tilde to be is, fix this X and answer about this particular X. Okay, we don't answer about every possible assignment to the variables. We answer about this one assignment that is supposed to be satisfying to E, which in the good case it exists. In the bad case, there is no such thing. Okay. Okay. Is the intuition for doing each check with probability a quarter that this effectively checks all 4 conditions simultaneously? Very much so. This is exactly what we're trying to do, right? So if I have a check that I do everything with probability 1/4, and I know that this test accepts with extremely high probability very close to 1, in particular, each one of the 4 accepts with very high probability, and this is what I'll use. Yes, good. Yes. Any other questions? Okay, good. So this is the construction. Okay, so if you're happy with a weak PCP theorem, this is the entire transformation. This is pretty amazing. What I'm going to do in the next 15 minutes is explain to you how you analyze this construction. Let me start a new whiteboard. Okay, so the analysis. And of course, I'm going to not do it like all the way, but hopefully you will come out of it knowing how you analyze it. Why is the last equation some RIEI plus Q, and not just some we'll talk about that. We'll get to it. It's a good question. No, okay, I can answer. So I wonder if I can go back to. So there was a last question, which is why in the fourth test, why do I need this extra Q? And the issue is that I don't control the E's, right? The E's are arbitrary equations, and then RIEI is some random linear combination of them, but also the random linear combination it's a very small portion of all my quadratic equations. So we'll see this. I mean, it's possible that the assignment for just this linear combination sigma RIEI, it's possible that this assignment is completely wrong. So to show that this equals 0, I mean, the prover may achieve that without any kind of consistency with some global assignment. And that's why I have the Q to kind of, Q is completely random. On a random quadratic, I'll show that it behaves well. And okay, let's see it on the next slide. When we'll see the analysis and we'll discuss all those things. Okay, so analysis. Okay, so the kind of the bulk of the proof, and also the one thing I won't have time to show you in full is what we call linearity testing. So linearity testing is exactly this test one, right? So L1x plus L2x is supposed to be L1 plus L2x. Okay, so this is what I call linearity testing. I do it for random linear functions L1 and L2. And what I'll show is that if test one, which is this, right, passes with probability at least 1 minus delta. Delta, think of it as a very small constant, 0.001. Then there exists x in 0, 1 to the n, such that for at least 1 minus delta a fraction of the L's, we have Lx actually equal Lx. Okay. So so before I asked the provers to I asked the assignment to give me supposedly the evaluations of all quadratic or linear functions on some x, but they didn't know that they did it. And in this part we're saying, yeah, but if we check this test one and it passes with high probability, it means that there exists an x such that they had to answer accordingly. Okay. Okay, we fix this x. So this is kind of the bulk of the proof. Kind of why, if you have those local tests, right? L1 plus L2 equals L1 plus L2. Why it actually corresponds to a global linear function. I know of two proofs for that. One is that this is one of the easiest proofs you can get with Fourier analysis. If you just write everything in Fourier, right, you can think of this test as checking the correlation of the function with a convolution of the function with itself. And you end up just getting there the sum of the cubes of the Fourier coefficients, and each Fourier coefficient corresponds to a different x, and if the sum of the cube is large, then there must be a dominant x. Right, so it's for those of you who know Fourier analysis, I mean, this is very easy. And also you can just prove one right in an elementary way. Yeah, so right, so what would you would say is yeah, I don't know if maybe you can prove it elementary and not let's not actually do the proof right now because I'm running out of time. But in a way, maybe this is the kind of the bulk of the proof. Okay, if I have time in the end, I'm happy to answer questions about linearity testing. Okay. So this is the first thing. So this is the kind of for the one thing for the one part of the test. The second is again linearity testing. Similarly, right, we do this test not just for the linear functions but also for the Qs. and right, because of test 2, if test 2 passes, so test 2 was Q1 plus Q2 equals Q1 plus Q2. Passes with probability, very large probability, then there exists, now it's going to be Z in 0, 1 to the squared, such that for at least 1 minus delta fraction of Q, we have Qx equals, let's suppose that Q is some Qij xi xj. This is some Qij zij. Okay, so we can also deduce linear structure on the Q because we also do this linearity test on the so this is for some Z. In 0, 1 to the n squared. Okay. So it's the same. It's application of the same lemma. One's applied on the L, one's applied on the Q, right, out of different dimensions, n versus n squared. But otherwise, it's exactly this. So now let's go over the third test. So this is what's called Rival's test. So the claim is if additionally to 1 and 2, test 3 passes with probability at least 1 minus delta. And let me remind you that test 3 is the one that checks that L1 times L2 equals L1 times L2. So if this test, the check consistency between the linear functions and the quadratic functions, if this passes with probability 1 minus delta, then in fact, we have with probability at least 1 minus, then with probability at least 1 minus order delta, we actually have that Qx equals Qij xi xj, right? So a conclusion similar to what we had for one. For one, we had it for linear functions. Now we can get it for the quadratic functions. That Qx actually behaves like Qij xi xj for the x that we fixed in the one part of this analysis. This actually happens for most Qx's. Okay. Okay, so I can actually explain the proof of this. This is quite easy. So what we have from so what we have from 2 is I have this matrix Zij that I know corresponds to the Qs, and the question is whether this matrix actually equals the matrix Xi Xj, and if it equals, then exactly I get this Q behaving the way it's supposed to behave. I see a question. Is the PCP algorithm practical algorithm that could be used in settings such as automated verification? Yes, it actually is used in verification. The issue is, you know what? Maybe let me return to this when we do the summary in the end, and let's first finish the analysis. In 2, checking a delta proportion of 0.1 to the n squared requires still exponential time, right? If so, why it helps? Again, right, so this is a weak PCP theorem. E tilde is of exponential size. Okay, so yes. However, to actually generate an equation, you can do it in polynomial time. If you are able to access bits of this huge exponential size proof, again, if you have random access to them, you can just check in polynomial time. But yeah, it's an exponential size construction. That's why it's weak. That's why I'm not proving the full PCP theorem. Okay. Yeah, and I'll return to applications. Okay, so in 3, all we're trying to do is show that the Zij matrix is the same as the Xi times Xj matrix, and if it is, then 3 follows from 2. Okay, but let's remember what test 3 does. So you can think of test 3 as taking right here, right? We take L1 and L2. You can think of L1 and L2 as, think of them as vectors, right? Put the coefficients of L1 and the coefficients of L2 as vectors, right? Each of them, these are matrices that are n by n, and each linear function has n coefficients. So really, what we're doing in test 3 is checking this equality. This is what test 3 is all about. And one can see that if the Zij is different than Xij, then with, right, you're going to have here, they're going to be different with probability half, and they're not going to be the same with probability close to 1. Okay, so this is the proof. Good. So this is the third portion. And now finally the fourth portion, and I remember that I still owe this answer for why we're adding this weird Q in the end, and hopefully you'll get your answer here. So this is what we call self-correction. So let's talk about our situation in this point of the analysis. So we asked the assignment to E tilde to actually evaluate each and every quadratic polynomial on this good X solution for E. And because all those 1 to 3 tests happen with high probability, I now know that I pick some X already in step 1, and I know that when I look at QX with the quotation marks, I actually get Q of X without quotation marks for most X's, for most Q's. Okay, so this is what we achieved so far. Okay, but this is true for most Q's. This is true for 1 minus order delta of Q's. It's not true for every single Q. Okay, so if I pick a random Q with high probability, quotation QX equals QX. But if I look at any particular quadratic form, this may not be the case. And the issue is that some EI RI is a very specific quadratic form, right? EI are my equations from E, and Ri are just like random coefficients, 0, 1 coefficients. So this is a specific quadratic form. I cannot rely on this being what it's supposed to be. So here is the trick. So this is what we call self-correction. Instead of looking at this, I'm looking at this plus Q, right? And I'm looking at this entire quadratic form. And now because of this Q, I made this quadratic form just a random quadratic form. So with high probability, this is going to be equal. So with probability 1 minus omega of delta, this is actually equals to sum EI Ri plus Q of X. right? This is what I achieved in 1, 2, 3. And now I check, right? So this is test 4. I check whether this equals QX. And again, with high probability, this equals to QX. This is what I achieved in 1 plus 3. And the conclusion from both of those things being equal is that the sum EI Ri actually equals of X actually equals 0. I don't know. I mean, I can't see it on the screen. I can see it on my iPad screen. I can't see it on your screen. I hope that it's fine. Okay, and this is what I wanted to check, because if one of the E's wouldn't have been satisfied, would have been equal 0, then a random linear combination of them would have been 0 just with probability half. But if it's 0 with probability close to 1, then it must be the case that all of the EIs are 0. Each and every one of the many, many EIs. That's it. This is the analysis of the PCP theorem. Okay, so I'm very happy to answer questions about the analysis. We started a bit late, so and if there are no questions about the analysis, I'll answer the question that I was waiting to answer. If I move my cursor away from the Zoom window, where is my cursor? Yeah, but then I won't be able, if I move my cursor away from the Zoom window, I won't be able to show, to see your questions and answer them. But yes, you're right. Let me answer the question of, is the PCP theorem practical? Okay, so, okay. The piece, right, I showed you this week proof. It's a very simple, short, nice proof, but it's this huge construction. Right, you need to work much harder if you want to show an actual polynomial size construction of G tilde or E tilde. And for many years, people were saying, oh, it's not practical, because even if it's polynomial size, it's a large polynomial size. This is no longer true. I mean, for 20 years, we have constructions, extremely good constructions of PCPs, transformations where G tilde is almost linear in the size of G. We also have nice, simple, relatively simple, simpler proofs of the PCP theorem. And we have kind of good understanding of how to prove PCP theorems. So, I mean, I would say that it's basically practical. Interestingly, what's actually being used by people in security, by people in systems, there are people in academia who try to apply those tools, and what they ended up using is mostly what I showed you today. Just this exponential size construction that still has like a very simple check. So yes, it can be used. It is used. I hope that it will be used even more. Yeah. Wait, is the PCP theorem used to construct efficient proof search? No. So the PCP theorem kicks in when you already have a proof, and the proof is written, right, in completely formal way, right? You have the solution, right? If it's pre-coloring, right? You have pre-coloring, it's very clear what's a procedure. If it's a proof, it's written in the axiom system, and there is a clear procedure to verify. If there is a proof, now you can go and check it very, very fast, but it doesn't tell you anything about how you find the proof. Okay, just a way to check. I mean, I guess if you're looking for a proof, you can try it. Right now, you have this quick way to rule things out. I mean, but you still need to search for the proof, which is hard. What additional steps are necessary to get to the point where PCPs are actually used to verify claimed proofs of the Riemann hypothesis? Again, so the problem with verifying proofs for the Riemann hypothesis, you need the original proof to be written in the axiom system, completely rigorously, right, in the axiom system, and then you can apply everything in an automated way. No one writes proofs in the axiom system, right? No mathematician writes in such low-level way. But if you do write things in low-level way, because maybe you use the computer to find your proof or something, I mean, then at this point you can use the PCP to quickly verify.
Okay, can I ask a question also?
Yeah,
they keep popping up more questions in the chat.
Yeah, I think I may be having a hard time keeping up, but can you give a high-level summary of what we proved and how it is related to what we wanted to show? Okay, let's go back to the whiteboards. So this is the proof of the PCP theorem, right? There is a transformation from every three-colorable graph to three-colorable graph. Not three-colorable means far from three-colorable. What we showed is this. So we showed it for quadratic equations, that it's very easy to move between quadratic equations and three-colorability. This is what theoretical computer science did in the 70s. And I mean, if you want to talk about it more, we can talk about it more. But the main thing is that we didn't show a polynomial transformation from G to G tilde. So what we showed is that so G tilde is exponential size, and every edge of it can be computed in polynomial time. Okay, which is nice, which is useful. It's truly useful. It is used in every proof of the PCP theorem and also in practice. But right, it's not fully polynomial. Okay. So this is
can I ask a related question actually?
Yes.
Which is actually sort of a question from Nike. You mentioned a connection between having a polynomial size proof and having a system where you can generate a single equation in O log n time.
Mm-hmm.
Right? Is this like an if and only if? And also, I guess, like, is there any other motivations for wanting to generate like a single one instead of generating the whole proof?
So, okay, the fact that you have a polynomial number of local tests, which corresponds to logarithmic randomness. I mean, this is if and only if you want G tilde to be polynomial in the size of G. The fact that you can generate, right, the PCP theorem, some of the strongest PCP theorems show how to generate it in polylogarithmic time. I mean, for this you need to work. This is not clear, and there are PCP theorems that don't generate a single test in polylog time. They generate it in polynomial time. They first generate the full G tilde, and then you can go and pick edges from it. Okay. More questions.
Actually, Dana, maybe just, I'm still not sure I understand. So in your construction, E tilde is actually the collection of all equations that can arise in your 1, 2, 3, and 4.
Yep.
Okay.
Mm-hmm. And it's a gigantic exponential, like 2 to the n squared size construction. Yeah, but it's locally it is efficient. Like you can generate one equation in polynomial time in the size of the theorem. Okay, let's see if I have more questions to answer. Why is quadratic sufficient? Do we need higher order equations? So this is okay. Quadratic is sufficient because you can formulate and or and not with quadratic equations, right? If you want to say the end of two things or the or of two things, or right, or it's just quadratic. So you can take any property any property that you can express in logic, and you can express it as a system of quadratic equations. That's why quadratic equations suffice. Okay. So in particular, right, so this is true for anything. It's true for free coloring. It's true for any property that you can express. Right, this is the Cook's theorem in right, the basis of NP completeness, that being able to express a property in first order logic, in propositional, right, in just and or not, right, this is equivalent to the property being checkable, that you can formulate the checking with just a logic expression. Yeah, so this is why quadratic equations are enough. We don't need higher order equations. We can formulate higher order equations with quadratic. I didn't understand why only few equations in E are unsatisfied, many more in E tilde are unsatisfied. This is exactly what, so this magic happened in the very last part of the analysis, where somehow we started, right, so in the entire analysis, we only know that a large fraction of the equations are satisfied, and yet the result in the end was that a random linear combination of all equations is satisfied with high probability, which means that each and every one of the equations is satisfied. Right, so this is this kind of easy probabilistic claim that if you have E1 to En and one of them is not satisfied, even if just one of them is not satisfied, the random linear combination is going to be 0 just with probability half. So this is where this magic happened, where we move from all the equations should be satisfied in E to just many of the equations are satisfied in E tilde. Okay, wow, lots of questions. Okay, discuss more the equivalence of free coloring and quadratic system and potentially 3-SAT. Again, hopefully it's clear that with quadratic systems, you can encode end, right? Because end is x1 times x2, right? And if you can do end, then you can do not, and not is just 1 plus x, right? And if you have end and not, then you also have or, and you have, you know, full Boolean logic. So now free coloring, right? You can write a propositional formula that tells you that, right, it takes, you know, those 2 bits that represent the coloring on one end and the 2 bits that represent the coloring of another end. And, right, you need to check that whether they're not equal, right? You can write a formula for that, right? So either the first bit is not equal or the second bit is not equal, right? Everything can be described in propositional calculus and right as a logic formula, and hence as a quadratic equation. Okay. Hopefully this explains it. Can a more efficient algorithm be obtained if there is some known structure in the provided proof, e.g. if it is decomposed into lemmas somehow? Wait, I'm not exactly sure if provided proof means the assignment to E tilde, or it means my proof that argues about E tilde. I don't know how to improve, how to get a more efficient proof than the proof that I showed you. Right, and obviously getting a more efficient construction of E tilde is kind of would be a huge right. If we had a proof of the full PCP theorem that was this level of difficulty, right, would be great. So if you could get a more efficient construction, that's great. I just don't know how to do it. Let's see what happens when you apply PCP construction to problems with obvious decisions, but no known solution, finding problems like factoring. Okay, so notice, let's go to the first whiteboard. So we start with checking some property. Here it's recolorability. The question is, what if I check if something has a factoring or not, right? If I check something easy, or at least it has a decision and doesn't. I mean, to check whether something is prime or not, right? We have a decision procedure. The issue is that if I can distinguish between those two efficiently, then my transformation can just, distinguish, understand what's the answer for the input, and then just have two different GTLs of like constant size that one is colorable, or one is prime and one is not prime. Or I'm not sure what does it mean, far from prime, but whatever you want to map it to, and right. If you can decide this in polynomial time, and you have those two constant fixed instances, one in the that is colorable. Actually, now that I think about it, I should use some highlighter. Yes, good. If this property is easy, if you can distinguish between this and this in polynomial time, then you can do it within your polynomial time procedure, and then just have two fixed instances here. And if the answer is this, output this, and if the answer is this, output the other one, right? So everything trivializes if you have a decision problem with an efficient solution. At least the theorem as stated here trivializes. Okay, I mean, good. Answer this. What is the resulting analog of GTL for factoring? I don't know. I don't know. Right? I mean, you have to map to something where there is local structure. If you don't have local structure, I don't even know what to do. Is there a reference filling in the proofs of correctness of the tests? Yes, so there is a book by Sanjeev Arora and Boaz Barak, Modern Complexity Theory, I think it's called. And I believe that it has the construction that I showed you today in the book. The book is available online. You can go and read it there. I think that this was the last question. So this is it.
Okay, so thanks very much for your talk and for your patience in answering all our questions. So now we go to a short coffee break, and you can join further discussion in Discord. And I believe we resume in 10 minutes.
Okay, thanks.